طيب, Bismillahirrahmanirrahim. Today we're going to start talking about IP version 6. As we said, IP version 6 has been the revolutionary approach to solve the problem of IP address shortage. So first we started with some incremental solutions like CIDR and NAT and PAT and address reusability and so on, and VLSM, of course. In parallel to this, people have been working on trying to solve the issue of IP address shortage fundamentally by designing IP version 6. Of course, IP version 6 was designed based on the lessons learned from IP version 4 issues. One of them is, of course, the quality of service. So quality of service was not actually supported in IP with enough granularity, and the reason is because IP is by default connectionless and it does not maintain any context about the flow end-to-end. So even though we can sort of provide some discrimination between the different types of traffic using the type of service field in the IP header, but we cannot provide any service discrimination based on the flow level. So I don't have any flow information. So that's why they started by defining what we call here the flow label. So this flow label provides an identification for the flow end-to-end. And this is quite different from what we have discussed before. Even TCP does not maintain an application-to-application label, although you can use the combination of source port and destination port together to form some kind of a flow label. But this is the first time we encounter like an explicit flow label that identifies the end-to-end flow, and that enables IP version 6 to provide different type traffic class based on each flow label. As you can see, the flow label is more than 16 bits. It's 20 bits, and based on that, you can provide up to 256 different traffic classes based on the flow end-to-end. So, which is good level of granularity and enough discrimination that you can provide using IP version 6. Of course, we talked about these intermediate solutions like CIDR and NAT and VLSM and so on. The new features that people have been focusing on for IP version 6 are first service quality guarantees, as we have just said. Service quality guarantees can be supported or provided based on the flow level, so we can, based on a certain flow, provide certain type of traffic class. So this way we have complete flexibility to provide whatever service discrimination that we need on the level of the flow. Also, end-to-end security is one of the features that has been provided in IP version 6, and that's because IP and the network layer in general did not support security initially, and that was one of the issues that if the routers are compromised, then the whole network is actually in jeopardy, and it's affected badly. Also, another issue which is quite related to the fact that we have shortage of IPs is the peer-to-peer networking. And by peer-to-peer networking, we mean that now we don't have to worry about NAT and PAT. We don't have to worry about address reusability. So each host on the internet can have unique address regardless of whether this is like a private network or public network. So there is no concept of private address, which means that we can assign a unique IP address on every single host on the internet. And that's quite useful because you can simply run any service on your machine at home and designate your machine to be a server, okay? Without having to worry about the fact that the IP address may change every now and then, because if it does change, then external hosts may not be able to connect to your machine in a flexible way. So if the IP address changes, then all the clients have to be informed, which is not usually practical. But here, since we are talking about a very large domain of IP addresses, we don't have to worry about consuming all these IP addresses, which makes any machine on the internet to work as a server with fixed IP address without having to worry about the fact that the IP address will change.
So you said the flow label.
Mm-hmm.
It's the same like of the one that is receiving on the other side has like the flow of control. You mean? In this
No. I mean that when a host connects to a host, they have different streams end to end. So this stream, it's like a virtual pipe that goes from one host to another host, right? So that's what we mean by a flow or a stream or an end-to-end connection. Okay, so basically TCP provides this application-to-application connection, right? But we do not have this information at the network layer, right? So for us, we cannot differentiate between the different streams end to end. With IP version 6, now we can assign a flow label from the connecting host, from the initial host. We can provide a flow label. That flow label goes to the router, and the router can then read the flow label and provide quality of service based on this flow. So even if you have multiple video applications, you can discriminate between them. For example, you can discriminate between video for a certain application that requires real-time streaming versus video that does not require real-time streaming. So both of them are applications that use video, but you still can provide some service differentiation between the two applications. Okay, so that's what this flow label is useful for. So back to the peer-to-peer networking. So now we don't have to worry about consuming all the IP address domains, and we can assign unique and one single IP address for each machine, in which case the machine can work as a client and a server without any restrictions. So that's useful, especially for peer-to-peer, because for peer-to-peer, as we said before, each host is by default a client and a server at the same time. So if your IP address is changing, then your peers would not be informed, and in that case, they may not be able to access the service from your host. And that might create some service disruption or some interruption to the service. So IP version 6 does not have this limitation, or in the future, it will probably not have this limitation. Okay, so these are the three major features that sort of identify or IP address version 6 tries to solve fundamentally compared to IP address version 4. As we said, IP address version 6 uses 128 bits. And of course, the dot decimal notation, remember we talked about the fact that the IP address version 4 gets identified, or it's usually represented in dot decimal notation. So we have 123 dot something, and so on. So, of course, with this number of IP address, it would be very prohibitive to use the dot decimal notation for IP address version 6, and therefore they use what we call the hexadecimal notation. So because in hexadecimal, you can represent this huge number of bits using fewer digits. So although it's still not readable easily, but it's much better to read. Okay. Okay. So based on that, of course, all the routing protocols, all the protocols in the network layer had to be redesigned completely. So, for example, OSPF. OSPF is one of the dynamic routing protocols. We did not, of course, cover it in details, but this is one of the dynamic routing protocols that had to be, completely redesigned because of IP address version 6. So there is RIP version 3, there is OSPF version 3, there is EIGRP. All these dynamic routing protocols had to be redesigned to deal with IP address version 6. And of course, as part of this, of course, we have to also support or process the flow label and the new traffic class label in order to provide some service guarantees. So this is part of the dynamic routing protocol. This is part of the packet forwarding. So when we forward a packet from the router, we have huge amount of packets in the router buffer, right? So which packet to forward first? So to provide some service differentiation, we now can use the traffic class and the flow label to sort of prioritize which packets to forward before others. So this way you can provide some different quality of service or some service differentiation. Cmpe version 6 is also the IP address version 6 version of the ICMP. We'll cover ICMP protocol today. Which is used basically for pinging between hosts, which is the one that we will talk about next. So ICMP protocol is a layer 3 protocol, although it works on top of IP. So if we were to understand logically where ICMP fits, so we have the transport layer, here, and we have the network layer here. So in network layer we have IP. Okay, so IP address, our IP protocol works as a service in the network layer, and here we have the data link layer, right? So ICMP fits here. Okay, so it's still in the network layer, it's still in layer 3, but on top of IP. So it actually uses IP. Okay, unlike TCP, which is totally in layer 4. Okay, so ICMP is a service that runs in the network layer, and it uses IP. Okay. So that's how it looks like. So we have the data link layer header, and we have the IP header, and then we have ICMP message. ICMP, as we said, it's used for ping and trace. Ping is used for troubleshooting if you want to decide, or if you want to verify whether a remote host is actually running correctly or not, and listening to your calls or not. So ICMP message is very simple. It has mainly a type and a code, and the rest is actually just a normal protocol fields, just to maintain sequence number and check the normal standard stuff that we have talked about before. The most important two fields are the type and code fields, and the type field indicate the type of the message. Again, ICMP works based on request reply. So the request takes, for example, type 8, and the reply takes type 0. Okay, and based on the reply, the reply may be, I received your message correctly, or it may be that, there is some error. In case of error, then the code will indicate what this error is. And the code could be any one of these possible values. Okay, so in case that the incoming reply is an error, then the code will indicate what the error is. For example, the destination network is unreachable, destination host is unreachable, and we will discuss the difference between each one. Okay. So again, ICMP, or the Internet Control Message Protocol, it works in layer 3, and it's used for sending messages, and it gets encapsulated into IP header. Okay. So for example, one of the error messages could be unreachable destination or service. Unreachable destination or service. This is if you send a ping message to a remote host, and then the ultimate router cannot receive any ICMP message from the destination host. So if the destination host does not send any reply back, the last router that's connected to the host will send a reply back. That's why it's layer 3. Layer 3 because the router itself handles ICMP, not the ultimate host. It's not an end-to-end layer 4. No, it's layer 3. So the last router before the message reaches to the destination will send a reply, an ICMP message back to indicate that the destination is unreachable. Okay. So this used to notify a host, the source host, that the destination or the service is unreachable. So when a host or a router receives the packet that cannot deliver, it may send an ICMP destination unreachable packet to the host originating the packet. So the host that's originating this ICMP request will receive a reply from the router, not from the ultimate host, from the router, that this destination or the service is unreachable. So if the reply came from the router, it would be a network unreachable, and that means that it does not have a route to the route table. So there are two possibilities here. So the destination is unreachable. It could be because of the fact that the router itself, the last router, was not able to deliver it to the destination because this destination is not existing in the routing table. Okay, so because the destination network is not in the routing table. So in that case, I will have to send a reply back that the network is unreachable. Okay.
And the host, it's not connected in that network connection.
Right. So
It doesn't have an end.
Right. So I'm trying to send to a destination which should exist on a specific network, and this network does not exist in the lookup table of the router. So in that case, the router does not have a specific route to this destination. So for us, this is destination unreachable, but destination unreachable because the whole network is unreachable. The whole network of that destination is unreachable. Or the host itself is unreachable. I have a route, but I cannot find the host. So I'm trying to connect, I'm trying to send this to the host, and the host is not responding. I cannot receive any appropriate reply from the host. So I found the route, I'm sending the packet on the network of that destination, but the host is not replying back. This destination unreachable may in fact come from the host. Okay, and the host can send. We'll talk about this in details later. So the host may actually reply back with destination unreachable, and that could have the two possibilities. The first possibility is that the protocol is unreachable, and in that case, this means that the TCP/IP is not running properly on that machine, and that's one of the things that you can use to troubleshoot whether the remote host is actually working correctly or not in terms of the TCP/IP protocol. Or the protocol is unreachable. Protocol is unreachable meaning that the application is not running. The application on that destination is not running. The application that is supposed to receive that message and reply back, this application is not actually picking up the message. Therefore, so the packet itself arrives to the host, okay, arrives to the network layer of that host, and then the host will say, okay, I'm trying to send it to TCP, but TCP is not actually working, okay. So that's one possibility. So in that case, we'll say protocol unreachable. Or I'm sending to TCP, but the application is not picking up. Okay? So if the application is not picking up, then we send port unreachable to indicate that the application is not actually responding back. So sometimes the application does not pick up the message because for security reasons the server does not want to respond to the ping messages. So for security, for example, if I send ping message to google.com, for example, okay, so sometimes the server prohibits the ping because some people might use the ping to as a source of attack on the server. So if you send, for example, 1 million pings in like 2 seconds or 3 seconds, then this will overwhelm the server and will delay and may actually bring down the whole server. So it may affect the performance of that server badly. So that's why some servers actually select not to respond to the host. And in that case, either the host will send protocol unreachable or the port is unreachable, that the application does not want to respond to your request. Okay. So one application that uses ICMP, which is the ping. The ping is a very simple application that sends a message as a probe message. I'm trying to probe a server to see whether this server is working or not. Many of us, if you work on developing a client and a server application, we use the ping a lot to test whether your server is working, is actually up and running or not. If ping responds back with a reply, then at least you know that your server application is running. Okay. Then if there is still a problem, this means that you need to go to the server and debug the code and see what's going on. But as far as the service is concerned, the service is actually up and running. So as I said, the ping works based on request and reply concept. So the source will send a ping request. It says ping and it mentions the remote address, and then the reply back will come with the destination is okay, is reachable. In that case, the code field will have 0. 0 means okay, everything is fine. If the code has anything other than 0, this means that there is a problem, and in that case, the number of the code identifies what the error is, whether it's protocol unreachable, network unreachable, and so on. Okay? So, so the ping uses ICMP, as we said, and in that case, if you remember, there is in the IP header there is a protocol field. Remember we talked about the protocol field, and we said that protocol field identifies the protocols in the higher layer. one of these possibilities is ICMP. So if the protocol field has the value 1, this indicates that I need to send this message to the ICMP service to process this message. And then ICMP will take this part of the message and will start processing the message to check the type and the code and so on. Okay. So ICMP does not use any of the layer 4 protocols. It's actually layer 3. It's underneath the TCP or UDP, so it uses IP directly. The ping is actually an application, a normal application, which when you say ping and then you specify the IP address, then the host itself will form an ICMP message, okay, in the layer 3, and then it will send it to the router. The router, by default, is configured to pass through the ping messages unless the router cannot find any route based on this IP address. So the IP address will indicate to the router the remote network. If the router has a route to this IP address, then it will pass it through. Okay, so by default, all the routers are configured to pass through all the ping messages. Okay, so the ultimate host may not actually accept the ping due to some security reasons, but that's another story. But all the routers on the internet, they are configured to pass through the ping messages. So the request will have a type field of 8 and a code of 0, of course, because there's no error. There's no possibility for error when I'm sending the request. So the echo request will have type 8 and code 0. We don't have to worry about all the other, because these are standard stuff. The sequence number will be set based on the message sequence number and so on. So this message, as I said, pass through one router at a time, will pass through all the routers, unless there is a router that cannot find a route using the IP address in this ping, in which case this router, because ICMP is layer 3, this router will send back a reply on behalf of the final destination. If the ultimate destination receives this message and it finds that everything is fine, the application is running, and there is a response from the application, then it sends a reply back. The reply back will have a type of 0 and will have a code of 0 to indicate that everything is fine, I did not have any problem, the destination is reachable, and the application is running, the protocol is running. So the ping, if it replies back, this tells you many things. This tells you that the router can route to the destination correctly. It tells you that the protocols are running correctly on the destination. It tells you that the application is actually running on the destination and it's picking up the message and it's replying back. So if there is a problem to send back like TCP messages and things like this, so the problem is in your code, or it's in the service or the application that you are using on the destination. Then the programmer will start debugging the code itself to figure out what the problem is. So ping sometimes may fail, and the failure could be like request timed out. And request timed out, this means that the destination may in fact receive the message, but it chooses not to reply to the ping request. So in that case, we'll wait and we receive a request timed out, which indicates that the destination is not replying back. So As we said, are pings forwarded by the routers? Yes, of course. Routers are configured to pass all the ping requests. So when we get something like this is because the device itself may not actually respond for different reasons, mainly for security reasons. Another very useful application, so if we send a ping request and then we get timed out, we get some timeout. So we need to figure out where that request was stopped. So we need to figure out what is the actual reason for this, because ping is really abstract. It does not give you any error code. So you need to know where this request stopped and what is the problem with that request. So in that case, we use another service which we call traceroute. Traceroute not only gives you the reply, but it gives you a reply from every single router that passes the ICMP request. Okay, so traceroute is another application that uses ICMP protocol, and what happens is that so the host sends that to a router, and then to another router, and then to another router, all the way up to the destination, right? So traceroute allows you to know that this request passes through this router. So this router will send you a reply back, and then the ICMP message will follow through this router. So this router will send you a reply back. So it's just that you trace exactly where this request is going hop by hop. So that gives you more information. So if for example this router replies back with an error, or it does not reply, or for any reason, then you know that the request stopped at this point. Then the network administrator will say, okay, so there is a problem with this network, so I need to go and see what's going on. Okay.
So, Doctor, this command, we cannot use it on our machine because we're
can.
version 4. IP version 4.
This is IP version 4. Traceroute is IP version 4, uses IP version 4. We finished IP version 6 خلاص.
I know, but yeah, you were talking about yeah, I think we were talking about IP version 6.
Yeah, we jumped. Yeah, sorry, we jumped.
Saying, like, this is related to which, so I thought it's for IP version.
Okay, yeah, okay, right. So okay. So it's maybe the mistake of the material. Well, so IP version 6 was just an intermediate topic, just to tell you that, okay, there is another approach that people have taken to solve the IP address shortage. But then that's it. Okay, so we finished that. We come back to IP address. Well, you can use ping for IP version 6 as well. Ping and traceroute, these are concepts. These are just applications that you use for troubleshooting. So whether it's IP version 4, IP version 6, it works on both. But these are not specific for IP version 6. Okay. So as I said, traceroute allows you to, from any point, to trace all this path one hop at a time to know where it stopped. So when we get to this point and we know that this point has a problem, then we know that the service provider at this point is not responding back, or maybe there is a problem with the network on that service provider. So if you have an agreement with this service provider, then you can call and say, what's the problem, and figure out a solution for So So because IP is a connectionless protocol and it's different, packets may take different path between the source and the destination. So IP is by default a connectionless protocol, as we said. So since we don't have any connection, then the requests or the trace route requests may take different routes at any point in time. Okay, so that's something that you need to keep in mind. So the trace route traces the possible route at this point in time. Maybe if you send another trace route after 2 hours, 3 hours, it may take another route altogether. So because trace route traces the route that the packet goes through, there is a possibility that you run it at different times and you get different routes. So if you run trace route today to a specific host and then you see like 3-4 routers, and then you run the same trace route next day and you see like 5 routers or 6 routers, I mean, don't panic. This is normal because IP is connectionless and it does not keep a specific route end to end all the time. So the packet may go through different routes. So trace will show the path that the packet takes to the destination, but the return path may even be different. So the forward path, or the destination, or the return path may be different from each other, because they may actually take different route, or they may take different routes at different times of the day, or at different days. So so when you do a trace route, you actually trace route the possible or the probable routes that the packet take to go forward and to come back from the destination. So this is the trace route. So when router A sends the Cmpe message, so I guess we'll stop here. So if people have any questions, we can.